Okay, folks, let's get started. Firstly, thank you so much, everyone, for joining in on a Thursday evening. I know it's pretty late, but I'm excited to see all of you here. My name is Pratik Kapasi. I'm the founder of HeyCoach. I have experience working in a bunch of product-based companies, and today we'll be talking about binary trees. So, before we dive deep into the data structure called binary trees, right? Uh, let's take a moment to understand why is it that DSA has so much importance? Right? Why is it that why are we even studying binary trees, binary search trees, stacks, queues, all kinds of data structures, fancy algorithms? Is it just to clear interviews with good companies, or does it have a bigger, better meaning to it? Right. So, and here's my perspective, which has evolved over uh, the past few years. Right. My perspective initially was that who uses these data structures? Why do we even need to study them? Uh, it's boring. It does not add a lot of value, and I don't like it. I don't want to understand this. Competitive programming, I'm not meant for that. Those kind of feelings. But as I went into the journey, I slowly started realizing that my hatred towards competitive programming or these data structures was arriving from the fact that I was not comfortable with it. Right? It was hard to accept, but I was not very familiar. I was not very comfortable working on these data structures. So what happened was the moment I started into this journey of solving problems, I started on this path of uh, problem solving. I slowly started getting a good grip over multiple data structures. Right? I did not enjoy it initially, but as I went into the process, I started mastering it step by step. And as I went into this journey deeper and deeper, I was able to conquer problems in different ways. I was able to solve problems in multiple ways, using multiple concepts, and slowly it started giving me the confidence. What resulted into that confidence, out of that confidence, was uh, I was able to crack interviews with a lot of good companies. I was able to, I still did not understand, by the way, why this was important, but I was able to crack the interviews. Right? Uh, as I proceeded into the journey, I realized that these top tech companies, a lot of good product based companies, they they don't just simply ask you these data structures and algorithms questions or competitive programming questions for the sake of clearing interviews, right? uh, they actually need those things as a part of their job role, right? Imagine working in, and this is an example I often give to a lot of learners, right? Imagine working at Google in the Gmail team, right? You're working in the Gmail team and you see the compose button or the send button there. Let's consider the send button, right? uh, you are working as a part of the team that is responsible for maintaining that send flow. The moment someone clicks on send, it is your team's job to make sure that email is sent to the recipient. Right? Now, imagine adding two lines of code over there that is making one database query. Right? Imagine adding two lines of code in the Gmail code, right? On the send button, whenever someone clicks the send button, your two lines of code gets executed and you end up making a database query over there. Now, what will happen is that those two lines of code, that particular piece, that snippet of code, is going to run for more than 1 million times a day because over 1 million people are using Gmail's send functionality on a daily basis. It is just two lines of code that you have added, but it is the impact that is creating the difference. So, one database transaction, one database query at that moment results into 1 million database transactions, right? So when you talk about scale, when you talk about data structures and algorithms, it is important because let's say instead of two lines of code, you have run a for loop over there. that for loop is going to run for 1,000,000 times. Now imagine a case where that for loop, which is going to take O of n of complexity, is not required. You could have done it in real time. You could have done it in O of 1, and you're making O of n, right? So the few seconds of computation that has increased because of you make running a for loop over there, which takes O of n instead of O of 1 complexity, results into that number getting multiplied by millions on a daily basis, which results into millions of dollars. So because the impact is huge over there, it creates a difference for them, right? And that is why they expect you to be skilled enough, to be competent enough to understand what goes behind those data structures, to understand how to write good code, how to solve problems in an optimal way, right? So that's where the data structures come in. That's where algorithms come in. And this is one reason why I think this is important. A second reason is that, let's say there is huge competition in the Indian ecosystem. There is huge competition for software developers, right? To understand who is the best developer, which set of developers fall into the cream category, the bar over the years have increased, right? And companies that are not using data structures and algorithms have also started asking questions over there. So that is one of the reasons that I feel has also led to the high competitiveness in the market, right? So let's get started with binary trees today. Let me present my screen. So I will be switching between two platforms. I'll be switching between a lead code playground, and I'll be switching between a Jamboard. Let me quickly open up a playground as well. So we'll be using C++ as a language to run a few piece of code. We'll run some code over here, and at the same time, we'll be discussing concepts as well. Even if you do not know C++, it's completely fine because I'll be explaining the algorithm. I'll be talking about the pseudocode as well. Right? So let's get started. So binary tree is a data structure, right? It's a data structure which has something called as the node. A node is a structure. If you take any language, let's say you take C, you take C++. Let me just increase the weight over here. Perfect. So let's take C, let's take C++, let's take Java, let's take Python, let's take JavaScript, any programming language of your choice, right? Most of the programming languages of your choice would have something called as the structure. A structure is a custom object or a custom data structure that you would create to store some kind of data, right? Now a structure could be, for example, if you talk about student, right? A student structure would have something called as the name. Let's say I'll have a string name, right? I'll have let's say a date object, which will be date of birth, right? I could have let's say another address object as a part of the structure, which will be address or current address. I could have uh, let's say another string or a long, which would be, let's say, mobile number. I could have a string which says email ID, and this could go so on, and this becomes structure, right? Why is the structure important? Because it holds all of these attributes into one label, which is student, right? So let's look at a structure where we want to store some data in a defined format, right? So when we talk about and these data structures are extremely similar. If you look at it, they're different in their own ways, but at the same time they have a lot of similarity, right? If you look at linked list, right? Linked list is a node which has a pointer, right? I'm storing a data called 5, and it has a pointer named next, which points to another node of the same type, right? I'm expecting you to have some information about what data structures are. In case you do not have information about, in case you do not have that uh, background about what linked list is or what binary trees are, it's completely fine. Just stick around and you'll soon start to follow. So what these data structures are is it's basically a structure. Right? If you look at this particular node, how a linked list looks like is 5, 10, let's say minus 7, then this points to 0, this points to minus 2. Okay? So these are pointers, and then this points to nothing. So let's say null. Okay? Now this is a chain of numbers: 5, 10, minus 7, 0, minus 2, that we have stored in this particular order. Right? Now these are integers, so this is a linked list that holds integers. Right? I could instead have another linked list that says that holds strings, for example. Right? Pratik. I could have another name that says Kapasi. I could have another name that says HeyCoach, and this could point to null. Right? So now this is a linked list that holds strings. It could be characters, right? And so on. Now, this is a linked list. At the same time, if you look at trees, what are trees? It has something called as the left pointer. It has something called as the right pointer. Now, it need not just have left or right. It could have multiple set of other pointers. Right? It could have, instead of, if it has two, we can call it left and right. But if it has multiple, we can just store it as an array. Right? We can store it as an array of pointers. So I could say that, I can talk about a node or a basic element in this particular data structure. Let me call it as node. Right? I can say that, listen, this node will hold an integer. Right? So I will say integer value. If I want to store a string, it will be string value. It could be string name, could be anything. Right? Whatever data you want to store over here. Right? After that, I could have a pointer object. Right? A pointer is not directly the data that we are storing. It is a pointer. It is a reference to the data. Right? So multiple languages use, in fact, C++ uses something called as the asterisk star, a reference, a pointer. Right? It points to the next node. Right? So let me just say next. This becomes a linked list node. Right? So how would a node data structure for let's say 5 moving to 7 moving to 10 look like? We'll have a node data structure which will say value as 5. Right? This will point to another node data structure, right, which will say my value is 7, which will again point to the next data structure. Right? So let's add a next pointer as well. Let's say if the address of this particular node in memory is, let's say, FF5576. Right? So the next pointer over here will store this particular address, FF5576. So this is how this pointer is derived. Right? It is again stored in the memory, but the next object, the value of the next pointer is going to point to the memory location of the next node. Right? At the same time, over here also, let's say there is 10, which is stored at a memory location of, let's say, EF, EF, EF. So over here, the next pointer will point to hashtag EF, EF, EF. Now, the address over here is just representational. What I'm talking about here is a memory block. Right? If you look at memory, right, let's say this is storage. You have stored 10 over here, you have stored 7 over here, you have stored 5 over here. Okay? Now, this particular node is stored in the memory. This is stored in the memory. This is also stored in the memory. Now, the address of this node, let's say ABC. So, along with 5, it will also store the next pointer as B. It will also store the next pointer as C, and the next pointer as null. So this is how it connects. So when you go to 5, it points you to the memory location of B. When you go to the memory location B, you find the next node, which is 7, which points you to the next location as C. You go to the next node, which is C. You go to, you find the data as 10, and you say that, okay, what is the next memory location? Null. So this is how it is linked. That is why it is called linked list. Now, the very same concept applies to binary trees as well, right? So let's understand what trees are, and then let's move on to binary trees and binary search trees after that. Right. So let's add some color. Let's start with trees. Okay. So what are trees? You have a tree is a graph-based data structure, okay, that does not have cycles. Tree is a graph-based data structure where there are nodes, there are edges, and there are no cycles. Right? So now if you talk about trees, there is a node, just like we had in linked list. Right? There is one pointer or multiple pointers. Right? If you have multiple pointer, you can call it a trie as well, but we'll not go into that. Trie. You see how linked list, trees, tries, all of these are connected. Right? If you have a set of pointers, it is trie. Right? Now, if let's say there are 3 pointers, it is ternary tree. If there are 2 pointers, it is binary tree. Right? If let's say I just have 2 pointers, this is called binary tree. Right? A binary tree has, because it has 2 pointers, we can label them those pointers as left and right. Because there are 2 pointers, we can label them as left and right. This is a convention, folks. You don't need to follow this continuously. Right? You can name them as A or B. You can name them as anything you like. So let's talk about binary trees. Binary trees are trees which have at most 2 children. Right? Any node in the entire binary tree will have at most 2 children. One node, it has 2 pointers left and right, and here it could have another node which will have at most 2 pointers left and right. Over here it may have at most 2 pointers. Let me just add one left pointer, and let me say this points to null, this points to null, and let's say this points to null. So this becomes a binary tree. Now coming to why do we need this particular data structure? Let's talk about what this particular data structure is. Right? We've understood what binary trees are. Let's look at this in detail. Right? Now let me create a data structure. Let's say 5. I have something as 10 over here, something as 15 over here. Okay? Let me add uh, 7 over here. Let me add minus 5 over here. Again, let me add 10 over here. Let me replace it. Let me say 12 over here, and let me say 30 over here. Now, this is the data structure. So how is the data stored over here? Let's take a look. So we have, if you look at the node data structure at this particular point, how is it structured? Let me see if I can maximize this. Okay, never mind. So how does the node data structure look like over here? There is value, which is 5. There is left pointer, which points to this particular node. There is a right pointer, which points to this particular node. So because we are denoting the pointers through the diagram, I will not talk about left and right. We will just talk about value. Right? And because we're left with just value, and value is also represented here, we will not talk about the entire node data structure, but we will represent the entire tree using just this diagram. Right? But this is what it translates to. It basically means that I have, when I talk about this particular node, I'm talking about a node data structure with value as 5, left pointer as this particular pointer, and right pointer as this particular pointer. Right? Cool. So let's move on. Now, when I talk about this data structure, there are multiple uses of this particular data structure. You can navigate through the data structure the way you want, right? This becomes the root. It's called the root. Why? Because you can, if you get access to the root, you can get access to the entire tree. You can move left, you get access to this. You can move right, you get access to this. You move left, you get access to this. Right? So you can navigate through the entire tree from the root. Right? You can navigate through the entire tree from the root. So you need to have a reference to the root data structure, to the root node. Right? So let's go back. Now this is what the data structure looks like, binary tree. Now there are certain ways in which we traverse through a binary tree. There are certain ways in which we traverse through the binary tree. But before we actually go ahead and uh, talk about traversals, let's go and implement this binary tree in one of the languages and see how it looks like. Right? So next we will talk about is going to be traversals. But before we come there, let's go to lead code and let's get hand on with a few things over here. Okay? So this is C++, folks, but uh, I'll be explaining the code. So even if you are not hands on with C++, it's completely fine. I'll be explaining you. So let's create a structure. This is a structure in most popular languages. This is something that is available. Right? Now I want to store integer. Let me store integer value. Right? If I want to store a string, it will be string. But let's for now stick with integers. Okay? Now let's create a left and right pointers. Right? So pointers in C++, it is a pointer reference. Right? It's nothing but it stores the address of that particular object. Right? As simple as that. If when you create a variable, the variable is assigned a memory block. Where do you store the data? It is stored on a memory block. Right? The address of that memory block is going to be stored over here. Right? The address of that memory block is going to be stored over here. Right? It is nothing complicated. It is okay to have a different convention. If you're not very thorough with C++ or pointers, it's fine. There's nothing fancy, really fancy about it right now. So this is how a data structure will look like. So for our example, how would the first root node look like? So this is the tree that we want to build. Right? How would the root node look like? We will say that this is the node. I want to have value as 5, left will point to uh, address of node with value as 10, and right will look like address of node with value as 30. This is how the node data structure will look like. Right? And if let's say for the last node, when there is nothing it points to, this will be null. This entire thing will be. So let's go back. Let's add a constructor. Constructor, let's say that the constructor is going to accept an integer, let's say x. Let me initialize this value with the value that I receive in the constructor. Let me at the same time initialize left with null, right with null. It takes a default value of null, but let's still initialize it. Okay. Now, while we build this in complex code bases, okay, when we create a constructor, a lot of times there are default values that it picks up. Okay. For example, let's say you're creating a student record. Right? I can say that int has relocated from a different city. instead of end, let me say bool. Right? So now what I can do is, in this, I can initialize it to false. If at all the student has relocated from a different city, I can create an object and set this variable separately. Okay? But for now, let's not worry about it. So this is how a node structure looks like. Now let's talk about, let's create a node data structure, node pointer. Let's say root is equals to new node. Let me say 5. Okay? And let me return 1 and 0. Sorry. Let me see if we are able to run this. Okay, there's a semicolon that C++ expects after the structure definition. Finished, right? So, so we have finished this. Right? Now we can add a print data structure and say root.print. Let me add a, uh, let me just say cout root of value, right? So it is, so we successfully know that we have stored a value of 5 in the root data structure, right? Now let's add one more. What was the tree that we had built? We have 10, 7, minus 5, 15, 12, 30. Right? 10, 7, minus 5, 15, 12, 30. Come over here. Let's say we want to create 10. Now we can write an insert function into the binary tree and start inserting things into left and right nodes. But for now, I'll just make it very simple. Let's say that we are creating node 1. Right? We've created this node 1 and I want to point the root node. Root of left is going to be node 1. Root of left is going to be node 1. Okay. So now if I print cout of root of value, it should still print me 5. Right? What's happening, folks? Let's take a quick pause into understanding the code, because maybe some of you are not from a C++ background and this might be a little difficult to understand. So we have a structure in place. The structure has an integer value. Integer that we are trying to store over here is 5. We have a constructor in place, which is taking an integer parameter x. That x is being assigned to value. There is a pointer that is of the same data structure type. Star basically means it stores not the object, but address of that object. Okay? It stores the address of an object which is of type node, and it is denoted by the variable left. So for now, let me just initialize it to null. Left and right both are initialized to null. So when I say root of node pointer root equal to new node 5, what this means is it is going to create a data structure with value as 5, left pointer as null, right pointer null. A very quick, interesting side concept that I would really want to touch upon, completely irrelevant to this, is there is a very interesting concept called serialization. Okay. What serialization means, folks, is that when you create these complex data structures, right, you want to send these data structures over the network call. Could be API call, could be gRPC call, could be any kind of function parameter exchange as well, right? But passing these complex objects with their complex definitions, because right now for a 3-parameter structure, the structure or that particular object, node object, is looking so complex. Right? If this is something which is sent over a network call, it will take a lot of space. It will take a lot of uh, computation, because a lot of times it is not just the structure that you're sending. There are function calls that you're sending. There are what do you call constructors that you're sending, right? Which is again function calls. There are destructors that you're sending, right? Then there are getters, setters, mutators, right? Lot of different types of function calls that go behind each object. So what happens is we serialize, we package it, we compress it, and send it. Right? A serialization allows us to send data quickly, allows us to send data without actually sending the entire structure, because serialization is a kind of uh, it's defining a particular format and transferring data in that particular format, which can be retrieved again at the source at the destination. So I might, serialize. Instead of sending this entire structure like this, I will probably define a serialization and deserialization logic and send it as a string. Right? A very side concept that I touched upon, not important for this moment. Let's ignore that and move on. Right. So this is how the node data structure is created. Now what you have done is created a pointer as root of left and pointed it to the new node that we have created. Right? We can create a third node, let's say node 2, and point it to the right. Now this is not generally how we create nodes, but to just get started, I am using a very simple example where we are creating nodes incrementally. Now you can also do a cout root of left of value. Any guesses what this is going to print? First it printed 5 and next it printed 10. So this is how you can start creating a tree. Right? Now you can define a proper function and say that you can define functions that actually perform some tasks and make this a little bit cleaner, saying create left node. I can say root of create left node and create right node. I can define these functions which will create those nodes. Where do I do that? I can do I can implement those functions over here itself. Okay. So this is better than creating those memory blocks over here as a part of the main function. Let the class or the structure itself handle those things. Right? So for now, let's just skip this. So this is how you can create a binary tree. Right? Now coming to traversals. Right? Traversals, folks, there are three types of traversals that are possible in a binary tree. Three types, any guesses? The multiple ways, but three popular types, I would say. First is pre-order traversal. Second is in-order traversal. In-order traversal. The third is post-order traversal. Right. Let's understand from that particular example of what a pre-order, post-order, in-order traversal means. Right? Now let's take a typical node for that matter. Wow. Right. Let's take a typical node for that matter. Let's say, let me just say node n. Right? It is pointing to a different node left. It is pointing to a different node right. This is how the structure is, folks. Each and every node in the entire tree is represented by something similar, right? Left can be a null pointer, right can be a null pointer, but it is at the end going to be something like this. Right? Now, let's look at, and without a doubt, each of these are the exact same structure. So you will have a pointer over here, you'll have a pointer over here, you'll have a pointer over here, you'll have a pointer over here. Okay? Now, if you just look at, and here there is data. You're storing some metadata along with the pointers at each node. Okay? Now, let's just look at how a pre-order traversal talks about pre-order traversal looks like. A pre-order traversal says, what are these traversals? These are traversals are a way to navigate through this entire tree. Pre-order traversal or post-order traversal or an in-order traversal. Right? By the way, there is something called as level order traversal as well. We'll come to all of these. So what a traversal talks about is a way for us to iterate or move or traverse the entire tree. So let's say if I were to write down this tree as a list of numbers, right? What is the order that I'll write these numbers in? I can write it in different ways. I can say 10, 15, 5, 7, minus 5, 12, 30. Right? I can choose a different order and I can say that let me start from the bottom and say 7, minus 5, 12, 30, 10, 15, 5. Now, there are different ways to traverse through a tree. There are 3 or 4 defined particular popular ways that are of extreme importance to us. Right? So, given a structure like this, if you talk about the node first, then the left subtree, and then the right subtree, this is called the pre-order traversal. If you talk about the node first, then you talk about the left subtree, because this is not just one node, folks. This in itself is an entire subtree. This in itself is an entire subtree. Okay? So what we're talking about is node, left subtree, right subtree. Node, left subtree, right subtree. So this is called a pre-order traversal where the node comes before anything else. Right? The node comes before anything else. Now, if the same thing, let's say you talk about left subtree, you talk about the node, and then you talk about the right subtree. If you talk about the left subtree, then you talk about the node, and then you talk about the right subtree. It is called in order traversal. Right? And as you might have guessed, a post order traversal would look like you talk about the left subtree, you talk about the right subtree, and then you come to the node. What do you mean by you talk about a subtree or about a node? What do you mean by that? You start processing that particular node in that particular order. Right? Let's take a real life example over here. Let's take a simple example. We'll come to real life examples. Let's take a simple example over here. Right? Let me say that I want to print squares of this particular entire tree. Right? I want to print the squares of this particular entire tree. How will that work? How will that look like for an in order traversal? Remember, in order is node, left, right. So first I will take the node, which is 5, process it. When I say process it, what do? I take the square of it because that is what I'm interested in. Okay? So let me say when I process 5, when I take a square of it, I get 25. So I'm talking about 25 over here. Right? Then once you've processed the left subtree, once you've processed the node, you move on to the left subtree. Once you move to the left subtree, what do you get? You come to this particular subtree, right? And again, this itself is a binary tree, right? So a pre-order traversal on this would look like the same. Node, left subtree, right subtree. So what is the node over here? Which is 10. Let me say 10, the square of this is going to be 100. Again, move on to the left subtree, right? When I move to the left subtree, what do I get? I get 7. Again, 7 itself has 2 pointers, left and right, both being null. What is the left subtree? What is the right subtree? Both are null trees. Right? So I process 7, which is the first node that I process. I get 49 as the square. I go to the left subtree, which is nothing, null. So I do not add anything. I go to the right subtree, which is nothing, null. So I do not add anything. So now I'm done with the left subtree part of 10. So now I move to the right subtree part of 10. Right? Just clear this. We had 100, we had 49. Now when I move to the right subtree over here, This itself is a binary tree, so I follow the same thing, node left and right. Node left and right basically means I process the node first, -5, the square of -5, 25. I process the left subtree, nothing. I process the right subtree, nothing. I'm done with this subtree, so I go back. I'm done with this subtree, so I go back. I've processed this, I've processed the left subtree, so I process the right subtree now. When I process the right subtree, I move on to the node. This is the node, right? When I'm processing this particular node, this itself, this entire subtree is a binary tree. So I repeat the same node, left, right, okay? Node left, right, square of 15 to 25. I move on to the left subtree. Okay? Now, when I move on to the left subtree, again, I see that it is 12, which is again a binary tree with two null pointers. So I process the node first, square of 12, 144. Left subtree, nothing. Right subtree, nothing. I'm done with this. I go back. I've already processed this node, left subtree, right. Again, the same thing. So 30 square becomes 900. So this is how I process the pre-order traversal. I hope you followed this. This is how you process the pre-order traversal. Right? Now, let's talk about implementing this pre-order traversal through a question. Right? We'll be writing code in another few minutes, but let's just take a moment to understand what does pre-order traversal actually mean. Right? We process node, left subtree, and right subtree. Let's take one more example very quickly, just in case you have not followed it so far. We'll take a simple example this time. Let's say 10, 20, 30, 5. Let me not have this node at all. Let me instead have this node. Let's say this is my tree. Right? How do I start? I start off with 10. Instead of squares, I'll just print the nodes. Right? So let's stick to pre-order traversal, folks. Pre-order traversal. I start with 10, move on to the left subtree, which is this subtree. Right? Then we'll move on to the right subtree. Right? So first, let's complete the left subtree, and then let's complete the right subtree. So 10, left subtree, I am at 20, so I had 20, left of 25. There is nothing to the left of 5, so null. There is nothing to the, let me write this clearly at the bottom. Yeah, let's say 10. Then I move to the left of 10, 20. I move to the left, 5. I move to the left, null. I move to the right of 5, null. I go back to 20, move to the right, null. I go back up to 10, move to the right, 30. I move to the left, -5. I move to the left, null. I go back to -5, move to the right, 7. Move to the left of 7, null. Move to the right of 7, null. Go back to 7, go back to -5, go back to 30, go to right of 30, which is again null. Go back to 30, go back to 10, and now I have nowhere to go. So this becomes the pre-order traversal. And because it is null, let's just skip them. So the order becomes this. So this is how a pre-order traversal looks like. A post-order traversal similarly would involve let's quickly do the post-order traversal as well. Post-order would be left, right, no, right. So left, so I'll not process 10 first. I'll move to the left subtree. Right, this. Not process 20 first, move to the left. Not process 5 first, move to the left. So null, right of 5, null, right 5 at the end, which is the node. Go back, right subtree of 20, which is again null, so I'm not writing it. Go back above 20, go back to the top. I'm back at 10. Now I have to process the right subtree. Go back to the left again over here, the right again over here, which is this tree. So 30. Node again, I'll not process directly. I'll go to the left subtree first, which is -5 and minus 5 and 7. Left of -5, null. Right of -5, 7. Again, not write 7 directly. Go to the left of 7, null. Right of 7, null. Come back to 7, write 7. Go back. I'm done with -5's left subtree, right subtree. So now I will add the node, which is -5. I'm done with the left subtree of 30, right subtree of 30, again null. So now I will write 30. Now I'm done with the left subtree of 10, the right subtree of 10. So now I will at the end write 10. This becomes the post order traversal for this particular tree. Right? So this is how you navigate through the entire pre-order, post-order, in-order traversals. In order I'm not covering right now. That is there for your self-work. So if we were to implement this entire thing as code, right? Let's see how this would look like. Right? Now, in the constraint of time, I've gone a little fast to explaining pre-order and post-order. But if you have followed well, great. If you have not, we will still cover this as a part of the code. Right? So now that we've understood how to write a pre-order traversal for a given binary tree, let's understand how to solve problems, how to write the code for this. Right? So let's consider a binary tree again. Let's say we have nodes as 5, 10, 15. Let's just take 3 nodes to start off with. Binary tree. This is a binary tree. You may have a subtree over here, subtree over here, a subtree over here, a subtree over here. Now, if you look at it, this is the root node, and this is the reference that we will always have. So, a pre-order traversal for a binary tree starts with the root node, and let's write this down: node, left, and right. This is the order that we follow. So we do something for the node, then we do the same thing for the left subtree, and then we do the same thing for the right subtree. This is the order. Before we proceed to the right subtree, the left subtree is completely processed. Right. So let's look at how we can process this. Right. So the very first step will be process node. Now this process can be any operation that we want to do on the node. It can be a print operation, simple print operation. It can be take the squares and print. It can be a compute and print. It can be add to a database for complex operations. It can be make an API call for complex operations. Right? Could be anything. You basically take the data for node and you process it. Right? And to keep it simple, let's just say this process operation in this case is just print node of value. Okay. This is what we are concerned about right now. So doesn't matter what the process operation is. For now, we'll just keep it simple as print operation. Okay. So the very first step will be to process the node. The next step will be to repeat the same thing for the left subtree. What are we doing over here? We are doing a pre-order traversal. So for the left subtree also, we will do the exact same thing. Let me just say pre-order traversal for left subtree instead of node. And third is going to be pre-order traversal for the right subtree. This is what we want to do. This is how we want to process. But here's the catch. Right? When you are completely processing the pre-order traversal for the left subtree, because it says node left and right, you need a reference to come back to right. So it has to be a recursive approach. Right. So that is where this entire operation is what we have defined here is pre-order traversal for root, for the node as root. So if I take, let's take a lead code example. This example, given the root node of a binary tree, return pre-order traversal of its node's value. Right? So we have a root node, right? What we want to do over here is we want to start processing the root node. In this case, it will be print. So let me just say cout root of value. But to start off with, let's understand the return values as well. What is the return value? Return value is not a print statement, but it is a vector. Vector, folks, is an array for C++. Right? It's a vector that holds the pre-order traversal for this particular. So instead of printing it, what we'll do is we'll define a vector and we'll start pushing it over there. Let me just say vector int result. I'll start processing the root node. How do I process it? Let me just say result dot pushback root of value. But then we are accessing root node over here, so we need to know and root is a pointer, so we need to handle the null case. So let's just quickly add a line for if root is equal to null, then what do? We return an empty vector, because if there is no root node, what is going to be the pre-order traversal? It will return an empty array. Okay. So this is what we did. Now we have processed the root. Now we can access the value because we know that root for sure is defined. Now what do? We then process the left subtree, which is going to be pre-order traversal of the root of. But the problem here is the moment you say root of left, it will define its own result. Right? And at the end, if we are returning a result, we need a better way to store this. Right? So let's just define a separate function. For now, let's just keep it simple and define vector int result outside instead of over here, so that the state of the result is maintained as we traverse through the array. Now, this will not define its own result, because when we had initially defined result over here, the moment I say pre-order traversal of root of left, it will reinitialize result, and the earlier result is lost. The earlier result is still in memory. So we need a way to capture it back again. So instead of doing this, let's just define a global variable for now to start off with, and I'll show you a different way, better way as well. Because every time you will not have the choice to define a global variable or a class variable. Okay. So we'll do it for root left, we'll do it for right. And as we proceed into this, how will this be processed? First, we process the root node. Then we move to the left subtree and we start processing the left subtree, and the root node is still in memory because the function call has not ended. Instead, we have gone into a recursive function call where we are doing the entire thing for the left subtree. Okay? We process the entire left subtree, we get the list gets added to result, and then we come out to the right subtree. So this is how this works. Hopefully this should work. Let's just quickly check. Yeah, let's submit this. Perfect. Okay. So now what has happened over here is we have written a simple recursive function call to write the pre-order traversal of a binary tree. Now, most of the tree problems can be solved using recursion. So having a good grip over recursion is going to be important. If you look at the structure over here, what are we doing over here? This is an elimination condition. This is the initial condition where you ensure that null pointers are handled well. Right? This condition also ensures that if at all, let's say given an example 1, 2, and 3, 3 does not have a left subtree or a right subtree, 2 does not have a right subtree, and 1 does not have a left subtree. So the moment you start processing the left subtree of 1, you will end up passing root of left, which is going to be a null value, to the pre-order traversal. When you pass that, what happens is you will end up getting root as null over here. So if that is the case, you need to return back an empty response. Right? Now, what is happening over here is, if you look closely at the code, while the code is correct and is working, is this the best way to write this piece of code? Probably not. Why? Because you're not making the use of this particular return type. You're not making the use of this particular return type. If, let's say, we'll not get into the discussion of which one is better right now. Let's understand a different approach to write the same question, write this to solve the same problem. Right? We have understood the problem. Let's just understand how to solve this. Right? How to write the code for this in a different way. Let's say I do not want this. Why? Because I'm already returning this, right? So how do I do it? Let's say I remove this. Right? Now I have a vector with me, which is the result. Right? So this is the return value. So let me just define a vector int result inside. This is going to be my return value. Push a value to it, and now I expect a result from the left subtree. Right. So let me define a temporary result over here, which will be, let's say, result left. And let me just define the same thing over here. Vector int result right. Now, what has happened is we have gotten a return type. We are, instead of using a global variable or a class variable over here, we are using the return type. What do we do with the return type? We know the answer already. We will run a loop. We will say auto value in result of left. What do I want to do with this? I want to push result dot push back in the very same order. I want to push. First I'll push left, then I'll push right, result right, and then I'll return the final result over here. So if in case this is empty, which is this case, it will really not run the for loop. Right? In case the right subtree does not exist, this for loop will not run. And this particular function will return an empty vector. Let's quickly run this and check if this works. Let's submit and check if all test cases run well. It does. Right. So what has happened is we have changed the definition of the code base over here. We have changed the definition of the function call over here, and we're using the return type instead of defining a global value. Now this is the entire solution using recursion. And folks, if you already know, recursion uses stacks internally. Recursion internally maintains a stack. Right? Let's just reset this and come back to the Django. Now what has happened over here is, now that we have solved this entire problem, let's take one more moment and understand what has happened. We are first trying to solve for, let me say, pre-order of 5 is what happens at the first. Once you start with this, you first process 5, then you process pre of 10, and then you process pre of 50. How does this work? When I say pre of 5, you end up processing 5 first, then you end up processing pre of 10, and then you end up processing pre of 15. Right? But before you process pre of 15, what really happens is you are already processing pre of 10, which will process 10, and let me just hold this function call over here, pre of 15. And it will process pre of 10, which will say pre of 10's left subtree and pre of 10's right subtree. Now, what is really happening is this itself will be a function call, and it is a recursive function call. So what is happening internally is the compiler internally keeps a track of this particular function call. That I am at this particular memory location. Let me store this memory location over here. That listen, I am processing 5 and I have these variables with me, and at this variable I'm jumping into a different function call with a different set of values. So it has stored 5 separately in a stack, not 5 but that particular memory location for the execution. Great. Then we move to the next one. So pre of 10. So now it will store the execution for pre of 10. That listen, when I move to pre of 10 of left, I still need to process a few things. So let me hold the address of these instructions in a stack. Let me hold the address of these instructions in a stack. The pointer to this will be stored in that stack over here. Right. So what is happening is, the moment you process 10 of left, 10 of left is over here, 10 of left, it will start processing it from here, and the moment it has processed 10 of left, it will start taking it out. That listen, I'm done with this, let me remove this. Then it will come back to 10, which is 10 over here. It will remove this as well. That listen, I'm done with this. Now I'm back to pre of 15. So this is these were the variables back then. Let me take all of these back again, and that is how it will empty the stack. So if we were to implement this entire thing using a pure stack, instead of using the inbuilt stack, instead of using the systems, the internal stack that recursion as a concept, as an algorithm uses, what about what about us defining that entire stack ourselves? Right? How would that work? Let's take an example. 15. Sorry, let's stick to the previous example. Let's say 5. Let's say 10. 15. Let me say -2, 7, 5, or let's say 25, and let's say 30. No particular order, folks. I've taken random values. Right. Now, if I want to maintain a stack, right, how will I do this? Let's say I have a stack with myself. How will this work? I have this stack with me, and let's say this is the bottom of the stack. So if the length of the stack is 4, the top pointer points over here. If the length of the stack is 5, the top pointer points accordingly. Right? So now I start processing. Right? I'll just use the stack to store the reference of the execution. Where is my pointer? So now I start processing 5. I first initially push the root node to the stack. Let's say the root node is 5. Right? Uh, the root node is 5. I'll take it out of the stack and I'll start processing it. The moment I start processing it, the first thing that I'll do is process 10 and then move on to processing 15. Right? So if I start pushing, if I push, let's say 10 first, and then I push 15 first, what will happen is I'll end up taking out 15 first, which basically means I'll end up processing the right subtree first. So instead of pushing 15 first, and instead of pushing 10 first and 15 next, what I'll do is I'll push 15 first and then push 10 next. Right? So what this means is, the moment I take something out of the stack, I know that this particular node, which was pushed last, will be taken out first, will be popped out first, and will be processed. Right? So let's repeat this entire thing once again. We start with 5. I want to process the node as 5. Right? So I push 5 to the stack. Now I take the first value out of the stack. I say that which is the first value? The first value is 5. Okay, let me process it. So I pull out 5 out of the stack, and the stack is now empty, but now I'm processing 5. How do I start processing 5? The first thing that I do is push the right subtree, because that is the last that I want to process. So I push 15 over here. Then I process the left subtree, which is going to be 10. So I pushed both of these to the stack. Right? Now I come out, I say that let me repeat the same thing. Right? Take out the first value from the stack, which is going to be 10. Right? I take out 10 from the stack and start processing it. How do I process it? I push the right value first, which is going to be 7. Let me just write 7 over here. So I push the right subtree, which is 7, and I then push the left subtree, -2. Right? Now let's come out. Uh, let's start processing the same thing. Let's repeat the same thing. I pull out -2. What is to the right of -2? Nothing. What is to the left of -2? Nothing. So I come out of the loop. And while we do this, what we do is the moment we start processing the node, we start maintaining an order for it. Right? So how would this entire thing look like? We start with 5, pushed 5, keep a note of pull out 5 from the stack, start processing it, right? So I pulled out 5, I wrote down I processed it, which basically means in this case I'm printing the value, push the next step, right subtree 10, push the left subtree, right subtree 15, left subtree 10, right? Again, let's repeat the same thing. Pull out the first value, which is 10, process it, push the right subtree, push the left subtree, come out of the loop. Let's repeat the same thing. Pull out the first value from the stack, -2, process it, push the right subtree, which is null, left subtree, which is null, into the stack. Done. Repeat the same thing. 7, nothing, left, right, nothing. So we come out. So now 7 is also out. Let's do the same thing for 15. And how will this work out? 15, the right subtree is going to be, let me pull out 15 first because I'm processing 15. Let me take out 15. I add 15 over here because I'm processing it. I take the right subtree, 30, add it. Take the left subtree, 25, add it. Now I come out of 15's loop. I process the element again. This time it is 25. So 25. Right subtree nothing, left subtree nothing. Repeat the same thing again. What is at the top of the stack again? 30. Take out 30 from the stack and process it. Left subtree, right subtree, nothing. So this becomes the pre-ordered traversal for this particular graph. Right now, this becomes the pre-ordered traversal for a particular graph using stacks. Let's see how we can implement this using a inbuilt stack. Right. So let's create a stack. Stack int st. For folks who don't know what this syntax is, this is C++ syntax, folks. It really doesn't matter what syntax you use. In your own preferred language, you create a stack. You initialize an empty stack. Right? What will we do next? We will, to start off with, we will say that I want to push root to the stack. Right? Because that was the first thing we did. We pushed 5 to the stack. Right? What do we do next? We start processing this. How do we start processing this? While stack is not empty, right? While the stack is not empty, what do I want to do? I want to pop out the first value. Before popping it out, let me just take the value in a node. What is the value? Stack.top. Let's do a stack.pop so that the value is popped out of the stack. So now I've read the value. I have that value as a temporary node with me, and I have also popped it out of the stack. What do we do next? We process it. What does processing in this case mean? It basically means pushing it into a vector, for instance. So let's just define that result vector as well. How would the result vector look like? Vector int result. It's an empty array, folks. It's a simple version of an empty array. Vectors are a little more advanced than arrays in C++. So let me just say result.pushback, which basically means is an array.push operation. Result.pushback is an array.push operation. So if you are using a different language, this is the language reference that you need to use. Result.pushback. When you say result dot push back, let me push the value root of value. But the moment we access root, or sorry, temp of value, because we are talking about temp, every time that temp variable is going to keep changing. The moment we access temp variable, which is a pointer, we need to ensure that we are handling the null pointer error over here. We need to ensure that temp is not null. How do we do that? Over here, what is temp? Temp is the top of the stack. So we are pushing a node to the top of the stack. We need to ensure that that either null values are handled at this case, but if it is a null value, we might as well not push it to the stack. Right? So we need to ensure that we only push non-null values to the stack. So we have pushed this. So let's just handle the case where root is not null, where root is null. So let me just add a condition that we added last time as well. If root is null, what do I want? I don't want to process the entire thing. If root is null, the final answer is also going to be null. So let me just come out of it. Okay. So now root is not null. So we know that the first element is never going to be null. We are successfully able to access this value, but we need to still be careful about pushing other values to the stack. Okay. What is the next thing that we want? We want to process the write subtree as we discussed, right? So when we say write subtree, temp of write is what we're talking about. But just as we discussed, temp of write shouldn't be null. So let's just add that condition. Temp of write is not equal to null. This is what we want to do. So this becomes a condition where we add it to the stack only if it is not null. And then let's do the same for left as well. Let's do the same for left as well. What is happening over here? We are technically pushing the right subtrees root node to the stack. We are doing the same thing over here as well, but instead of right, it is left. Folks, understand this one thing. Why is it right being pushed first and left being pushed next? That is because the moment you push this last, that is going to be the first one, which is going to be popped out. Why are we using stack? Because the moment you move into a recursive call, you need to store the reference of the previous call. Right. So we do this. We are already storing the result in the same loop. So this is an iterative loop. Result is over here. We have defined it in this particular loop. Result is not changing. New values, it will start accumulating. So this is it. Let's just return the result and check. So let's just run it and check. Now stack dot push of root. Now the problem is stack is defined as an integer. Instead of that, let me just write it as root pointer. So push created a problem because the stack was defined for an integer, but we were pushing reference to a tree node root pointer. Let's just submit this. And it's acceptable. So this is how you implement stacks. This is how you solve the entire problem using recursion or with or without recursion. But in either case, the extra space that is occupied is going to be O of n. Right? Why is it is going to be of the order O of n? Now, why is this O of n? Why is it not? Why is recursion taking O of n? Firstly, because it is internally going to maintain that state. Over here in the second approach, we externally maintain the stack. The system does that for us. The compiler does that for us by default the moment you make a recursive call. So it is not like if you're making a recursive call, there is no extra space that is being occupied. Another thing, the entire binary tree, in the worst possible case, can be a skewed binary tree. What is a skewed binary tree? Where let's say you just have the right nodes back to back, the entire array is just a right node of each and every node is just a right node of the previous node. Okay. What would happen in that case? You will get into a recursive call, recursive call, recursive call. You'll end up maintaining the entire array as a stack, which is where you'll use up the entire array. Otherwise, in a properly, let's say, balanced tree, you would never require n elements to be stored in the stack. When you do not require n elements to be stored in the stack, what happens is you are just storing the height of the height of the tree in the stack. So height of the tree is going to be log of n. How is it log of n? We'll talk about that separately some other day. But height of the tree, if it is log of n, we are only storing log of n elements into the stack. When we're storing only log of n element into the stack, the space occupied is going to be of the order of log of n and not of the order of n. Right? But there is an edge case. There is a case where the entire binary tree is completely skewed, and there are n elements, and all of them are at a different level. Right? In that case, you will end up making a recursive call for the entire and store the entire array as a stack over there. And in that case, it occupies O of n space. That is where the space complexity is O of n in both the cases. The time complexity, on the other hand, is still O of n because every time you take a node, you process it. In this case, the process function was a simple print statement, a cout statement, or a pushback statement. Like we were just pushing the element to the array, to the vector in C++. But in complex scenarios, it can be making an API call, it can be pushing it to database, it can be something else. So in any case, if there are n nodes, if there are n elements in the array, it is going to take me and let's say n being a very large number, let's say millions, my complexity is going to be of the order of millions. Right? It is not going to be constant time. So that is a very important realization, that it is not constant time, it is not log of n, it is not a guesswork over here. You need to process each and every node in the binary tree, and that is why the complexity of this particular algorithm is O of n. So I hope you had a good time understanding this. Folks, binary trees are one of the most important data structures. Binary trees form the base for a lot of other data structures: binary trees, binary search trees, binary search trees, binary trees. There are AVL trees, red-black trees, self-balancing trees. There are different applications for each of these. There is something called database indexing. So if you're searching in the database, binary search trees make it easier to search within a subtree. Right? Binary search trees make it easier to search within the subtree. Why? Because you don't have to look at the entire tree anymore. If it is, assume a balanced tree where numbers are stored in a particular order, and you're looking for a key, you don't have to look at each and every element. If let's say that entire structure is ordered, binary search tree, if you know what a binary search tree is, if you don't, binary search tree is a concept where the value of the root node is higher than the entire left subtree and lower than the entire right subtree. The value of the root node is higher than all values in the entire left subtree and is lower than all values in the entire right subtree. How does it help us? If I want to search for an element in that particular binary search tree, I look at the root and I know whether I should look at the first half or the second half, whether I should look into the left subtree or the right subtree. Right? So that is where this comes in. Searching becomes easier. Sorting becomes easier because now I can arrange the elements. I start pushing elements into a binary search tree and all of a sudden the entire structure is sorted. Right? Why? Because it maintains this property of left subtree, root node and right subtree in an ascending order. So database searching, database indexing, sorting, searching, there are multiple applications in real world frameworks where binary search trees come of extreme use. Okay? Not just this. Think of a scenario where if you know hash maps, if you know hashing, right? We push a value, it internally maps it to a bucket. Now, if let's say in case of a conflict, how are conflicts handled in case of a hash map? When you have one key, you have multiple values that lead to that one key, right? And at the end, all of them are stored linearly, right? Now, linear searching and binary search both are very different. At times, frameworks at times, popular languages have optimized that linear search over there to search. Instead of having a linear array-based data structure, they keep a binary tree or a binary search tree. Typically, a binary search tree, so that searching becomes easier. So now, if I have, let's say, 10 values that map to the same bucket, the same key, and I need to store those 10 values against that key, and if I'm searching for that value, if I'm searching for the value for that value against that key, I do not have to look for that one key linearly. I can use binary search tree over there to find that if that value exists or not, right? So now I'll not go into the details of how a language uses a linked list or a binary search tree internally, but understand this one thing, that this particular data structure is extremely important when it comes to searching and sorting, right? And it has a lot of real world benefits, not just in the database side of world, but if you generally look at a binary search tree, it gives you a decision making process, a decision flow, that what do you do this, what happens if you do this, did this happen, yes, no. If it is a yes, you look at this tree. If it is a no, you look at this tree. In very simple words, this is what binary trees and binary search trees are. Right? We've not gone into the depth of binary search trees, but that's for some other day. I hope you enjoyed the session. Thank you so much.